Previously, we've talked about logic functions, and just to summarize is that we have a logic function, for example, an AND gate, and we can draw it here, and this is the symbol for an AND gate. Let's say we have 3 inputs here. You can have as many inputs as you want, and then we want to have one output here, and an AND gate generally has one output, so we put a little dot here, so this is an AND gate. Well, what we find is the only time this output can be 1 is when all the inputs are 1. So this input is 1, this input is 1, and this input is 1. Because we're saying that the output is 1 when this input and that input and that input are all 1. If, for example, if we were to change this input to, let's say, 0 on the AND gate, then this would change to 0. Now, we also talked about we not only had AND gates, we had OR gates, which have that kind of pointy part on it, so it looks a little bit different than an AND gate. We had inverters, look like that. And so there's many different types of digital functions we had. Now, what happens when we can form all these digital functions with these digital logic gates, but what we can't do is we can't reliably store the information in our logic circuit with just digital logic gates. And this brings us to today's subject, and today's subject is the whole notion of state. How can we preserve state? How can we remember what was this state that our logic function was in between, let's say, one time period and another time period? The way we're going to do that is we're going to look at things called flip-flops. It's a wonderful name for these things. We'll explain what they do. And then we'll combine the notion of flip-flop and state, and we'll make counters out of these things. So we'll just see how all these things can fit together in some very simple examples. Okay? So let's see. Let's take a flip-flop. I think this is actually from Wikipedia. So a flip-flop, okay, is a device like we had an AND gate and an OR gate or devices. But this has 2 stable states, which means that it can be either a 0 or a 1. Those are the 2 states that flip-flop is. And then the flip-flop remains in those states, or it remembers that state, or stores the state until something happens to change that information, flip-flop. So it's storing state is the purpose of a flip-flop. We'll see, this is fairly abstract. We'll take a look at it a little bit later and see how this works out. Now, there's many types of flip-flops, okay? So we're going to use a type D flip-flop. For those who are interested, we have type T flip-flops, which are toggle flip-flops. We have probably the most generic or most widely used is a JK flip-flop. We have a set reset flip-flop. There are many, many types of flip-flop. I think the D flip-flop is probably the most useful and also the easiest to understand. So we're going to go after the D flip-flop. As with any flip-flop, is that we have a state, okay, and those states are presented to the output of the external world by 2 outputs. This output is Q, so Q can be either 0 or 1. And then you also have not Q, which can be 1 or 0. Now, formally, it's not necessary you have to get the output out, like in Q would do that by itself. But we have Q bar because sometimes it makes it easier to build the circuits around it. So this is a fairly convention. We have this output state. The other thing is we have, a data input. Let's make that a data input. D, which is sitting right here. We have a clock input, which says when does the data input affect the state. That's all the clock input does. We have a set input, which allows us to set the state to 1, and we have a reset input that allows us to clear the state to 0, to reset the state to 0. So we're going to use these inputs, and let's see, there's these 4 inputs together in order to change the state. Once we change the state, the flip-flop will stay in that state until we do something to change it again. So the state is preserved until new inputs change the state of the flip-flop to a new state. So let's look at the first set of signals, and these are the output signals. And I alluded to earlier, what it does, it takes the internal state of the flip-flop, which is either 0 or 1, okay, and it presents it to the outside world. So if this is the internal state, what it's going to do, it's going to present it to the outside world. So the outside world will see Q equals 0. If the internal state of the flip-flop is 1, the outside world will see Q equal 1. So what we have is we have a little table. So here's the internal state down in this column. And for this internal state, when the state is 0, we get Q equal 1 and Q bar, or not Q, is equal, I'm sorry, Q equals 0 and not Q is equal to 1. When the state is 1, it's just the reverse of that. Q is 1 and Q bar is 0. So that's why we can sense the state of that flip-flop. And so let's look at the set reset functions. Those are primarily used to initialize the flip-flop. So when the circuit first starts up, we'll use the set and the reset. So here's your set input, and there's the reset input to put the flip-flop into a known state. Okay, so let's see. When set is high, we'll have the internal state of the flip-flop go to 1, which means Q will go to 1. When the reset is high or active, and when I say high, I mean when this is 1, Q goes to 1. When the reset is 1, Q will be forced to 0. So let's see, the truth table tells us if set and reset are both 0, then there's no effect on the state. So these do not affect the state, so whatever Q is, it just stays. And this is how we indicate that, by just saying the state remains a Q. When set is 0 and reset is 1, then we reset the flip-flop. We force the flip-flop into the 0 state, so Q is 0. Conversely, when set is 1 and the reset is 0, we're telling we want to set the flip-flop, and we want to set the flip-flop to a 1. When both of them are 1, which is actually in many cases kind of an illegal state, we're going to set the flip-flop to 1. Okay, so we can use set and reset in this to just change the state of the flip-flop. So this may be a circuit that we have, and so let's look at this circuit. We have 4 flip-flops. Okay, so we have flip-flop 1, 2, 3, 4. And then what we do is we have the reset lines are all hooked together, and they're hooked through a resistor to 0. And then they're hooked with a switch, a momentary switch. This is just a push button momentary switch to 5 volts. So this would be a 0 when we're connected there, and this would be a 1 when that switch connects, because we bring it to 5 volts. Okay, so and the same thing happens to the set. We have this would be our set line up here. Our set line is normally set to 0. When we press this button, it will go up to 5 volts. So what can we do with this kind of circuit? Well, let's say that somebody momentarily presses S1. Okay, and that results in that this becomes 5 volts. And what that does is that means now all the sets are 1. When all the sets are 1, all the outputs, the Qs, are 1. Of course, the Q naughts will follow as 0 because they are the opposite of Q. Okay, so after we push this button S1, this becomes 5 volts, and then it goes into each of the 4 flip-flops go to that state. Now, let's suppose that we now let the button up. This now becomes 0 volts because we're no longer connected to 5. This becomes 0, 0, 0, 0. But guess what? The states are still 1, so Q is still 1 in each of these 4 flip-flops. So we can see how to set it. Now, let's go through and look at how to reset it. We do the same thing. In this case, we press S2. This becomes plus 5 along here. So all of the all the resets are 1. Resets are 1 means that this output be 0, 0, 0, 0. And then when We let go of the switch, so the switch goes back up. This returns to 0 volts, which is actually, we call it at 0. So the reset becomes 0, and then the state remains at 0, 0, 0, 0. So we can go through and use the switch S1. We can use S1 and S2 to set our 4 flip-flops either to set or clear. Okay. Now, the thing about these resistors is many times we don't use these resistors, but it's a good idea to use these resistors because this is generally ground. And then what that does is just make sure that when this switch is not pressed, S2 is not pressed, is that indeed we have zeros on this line. Okay, let's look at the D and the clock input. Now these work together. You can't talk about one without the other. Okay, so the D and the clock work together to change the state of the flip-flop. So you said, well, we already have a way of changing the state of flip-flop. That's set and reset. Well, this is a way of changing the state of the flip-flop at certain times, certain well-controlled time. Okay, so here's the rule. When D is 1, okay, is high, and the clock transitions from a low to a high, Q is going to go to 1. Now, what do we mean from a low to a high? The clock is generally a periodic function. It need not be symmetric, but it looks something like this. Okay? And so when we say we're going to transition, the transition from low to high is at this time. This is low to high, low to high, low to high. So D only affects the output Q, or the state of the flip-flop, during these transitions. Now, once you set the state of the flip-flop will stay until something causes it to change. So we have that. So what happens if D is 0 when the clock transitions from high to low? Okay, whoops, Q goes to 0. So I need to change that. Okay, so we go to 0. So QD tells us what the state of the flip-flop should be after this low to high transition. So we can put this together in a little truth table. And let's see, this truth table looks the following. When D is 0, and we have this transition from high to low, so this is what we do. And we're assuming that the set and the reset are all 0, so we don't care about it. Then Q is forced to 0. Okay? If it had been 0 before, it stays. If it had been 1 before, it flips to 0. When D is 1, at that transition, without the set or the reset being high, then Q goes to 1. Okay? Now, let's say that the clock is 0. Okay? So we're not looking at the transition. Then we ignore D, and Q just stays what it was. It doesn't change. If the clock is high, it doesn't change. If the clock is going from high to low, it doesn't change. So the only time this changes is the only time that D can affect the output is when the clock goes from low to high. It's this transition here. Okay, so we have that. Okay, so let's look at some really simple examples, okay, kind of fun examples. Let's see. So this is a flip-flop. It has a 1 for D, okay, and let's say the Q is initially 0. So this is time. These are all time, okay, and I'm going to call this as being a 1, and this is being a 0. This is a 1, and this is a 0. So these are these little waveforms. Okay, so what happens here, if Q is initially 0, nothing happens until we get a transition from low to high. At that transition, during this time, what we'd expect is because D is 1, we will flip Q from 0 to 1. Okay, now then nothing happens along here, because the clock is not affecting anything. And then the next time the clock goes from low to high, what happens is Q stays at 1. The state of the flip-flop stays at 1. Why? Because D is still 1. So this is just showing a very simple circuit and how it would work. Let's go through and do something a little more fun. And this is a circuit where we take the Q bar, or the not Q, and we feed it around into the D input. So let's see what this would do. Okay, let's assume again Q starts off at 0, and then this is the rising transition. So let's see, when Q is 0, what's Q bar? Isn't it 1 during this time? And so now D is equal to 1 during this transition, which means what? When D is equal to 1, Q goes to 1. Okay? So then we continue to go, we follow the clock until the next transition. At the next transition, what happens? Let's see, Q is 1. That means that Q bar is 0. D is 0. So what happens? We transition to 0. So what happens is that every time the clock transitions from low to high, because of the fact that we're feeding back to D the not state, or the opposite state of the flip-flop keeps on changing states back and forth. So this is an example of another circuit. Okay, let's do something a little more involved. Now, this gets a little bit, just watching these circuits can get a little bit wild. So let's take our time and see what this circuit is. We'll take it apart. Well, the first thing the circuit looks like is, let's do the set and reset. It looks like the first flip-flop, let me just go through a number of these flip-flop. 1, 2, 3, and 4. And let's see the outputs. This is Q1, this is Q2, this is Q3, this is Q4. Let's see, it looks like the input to a flip-flop is the output, or the state, of the previous flip-flop. Okay, that indicates these lines. And this one's kind of weird, because this one's going to come all the way back around to feedback in here. Okay, now let's look at set and reset. When we push this button, this 5 volts, okay, is that, and by the way, I left the resistor off of here. I should have probably done a better job. So here's my little pull down resistor to ground. When I push the button, resets become 1. So therefore Q2, Q3, Q4 will be 0. And then when I push this button, what happens up here? This set becomes 1. So Q1 will become 1. Okay? So, and what happens, okay, so we have that. Now let's see what happens when the clock, on the rising edge of the clock, this Q is going to be transferred to this flip-flop, because the Q is equal to the D is equal to Q. This state will be transferred to this flip-flop. This state will be transferred to that flip-flop. So I think we have kind of an understanding of what this thing looks like. Let's see if we can actually sketch the timing, the diagram on it. So here's time, okay, along here. Here's the clock, and remember what the clock does. It's the rising edge of the clock that will make a difference. So I'm just noting them down here. And notice we put a little kind of dotted line going up here, vertical dotted line for construction line here. And then what's going to happen here? When we initialize, okay, the clock, okay, initially we have no idea what Q1, Q2, Q3, or Q4 is. I go through and push that red button, or this button here. Initialization goes up. So what's going to happen? It's going to cause the Q1 to be 1, Q2 is Q1, Q2, Q3, Q4. Now, during this clock time, we still have the button pressed, right? Because this is still initializing along here. So we ignore that. So now we're just running over this way. Okay? So we stay at 1 for Q1, 0 for Q2, 0 for Q3, and 0 for Q4. Now, when we get the rising edge here, what happens is that Q1 assumes the value of Q4 because we have this network here. Well, Q4 was what? That was 0. Okay, so Q1 dives to 0. What does Q2 do? Q2, because of this line, goes through and assumes the value of Q1. What happens to Q3? Well, Q3 assumes the value of Q2, and then Q4 assumes the value of Q3 because of this line and that line, respectively. So we go along here where the flip-flop preserves the state until the next clock activity. And at the next clock activity, what happens? Okay, well, Q1 receives the input from Q4, so it's still 0. Q2 receives the input from Q1, so it goes from 1 to 0. Q3 receives the input from Q2. Well, that now flips Q3 up, and then Q4 receives the input from Q3, which stays at 0. And then we continue on this direction until the next clock cycle, and then Q1 will stay, because Q4 was 0, Q1 will stay 0. Because of Q1 was 0, Q2 stays 0. Because Q2 is 0, Q3 is going to become 0. And because Q3 had been 1, Q4 goes up to 1. And then we continue along there until this happens. Okay, what happens to Q1 right up in here? Q1 rises to 1 because Q4 was 1. So Q1 is going to flip up here. Q2 is going to stay down because Q1 was down. Q3 stays down, and then Q4 drops down here because Q3 was down. And so what we have here is we have a situation where, where what happens is that we get a 1 here through the set, and what happens, that 1 gets transferred to each one of the flip-flops in turns. See how the 1 gets moved? Each clock cycle, the 1 gets moved. Now, after the 1 is in Q4, what happens? The 1 gets transferred back up to Q2, and guess what? This thing repeats. Okay, and this is called a shift register, and specifically it's a ring because the thing's going around in a circle. This is probably a good time. Let's see, let me go on to this and we'll see if we should stop on the next one. Yeah, this is a good time to stop, and we'll pick it up on the next video.